we have seen, with the help of simple rules of chaotic, fractal and bubbles walls, that we can get rid of Bean's figuration and get out of the gluon hypothesis which bound quarks together. And we were able to define basic matter such as various forms of cycloid. And now, let's see why the proton and deuterium are surprisingly stable by using the laws of a fourth tool, the quasi-crystallography.
To summarize, the concept of quasicrystals appeared with the researcher Dan Schickman, who produced a metal alloy which had a 5-fold symmetry X-ray. In the classic and peaceful world of crystallography, where only existed the orders 2, 3, 4 and 6, the arrival of the order 5 was a real revolution. Indeed, one discovers in the microscope that crystals appear as dodecahedrons or icosahedral. But further down in this structure to better understand the following demonstration. First, start with the notion of paving. With squares, triangles or hexagons we can fill a surface without creating gaps, which is not possible with pentagons. However, resuming Roger Penrose's paving, we discover that we could approach the order 5. We then take two types of rhombus, one called fat with angles at 108 and 72 degrees, and the other called thin with angles at 144 and 36 degrees. And we can fill a surface without gaps and with an endless variety of patterns. And with the same logic using two types of fat and thin rhomboid, we can also fill the space 3D without gaps. Therefore, in the world of solids, between the crystal type well organized and the type of amorphous materials, we now include a third type of solid called quasicrystals that its X-ray is showing a symmetry of order 5. And when a conventional crystal shows an ordered diffraction compared with an amorphous solid, the quasicrystal shows the diffraction on quinary basis, where we find pentagons with growth following the golden ratio. Remember that the golden ratio is the ratio of length of the diagonal of pentagon divided by length of a side. This is an irrational number called tau or phi, which has a value approximating 1.618. Note that we find the symmetry of the order 5 in many areas. And this gold ratio is also used in the so-called Fibonacci sequence. In this sequence, the numerator of each fraction is added to the denominator in each stage of progression. And, ultimately, this ratio approaches more and more the value of the golden ratio. And what is interesting for quasicrystals is that their crystallization size is not gradually varies but is predetermined by the slots defined by parameter values. We find also that discontinuous progression with Penrose tillings for repetitive patterns. In this first example we see the repetition of a pattern of square size. With a ratio of 18 fat rhombus for 12 thin rhombus, we have the first step of 3½ on the Fibonacci sequence. Now with a second example of a much broader pattern square. We get a ratio of 52 fat for 32 lean, and therefore a fraction of 13/8, and thus a next Fibonacci step. Thus conventional minerals crystallize slowly continuously in a constant and unchanging environment over a long period, while quasicrystals are formed suddenly by shock of temperature and pressure, and by adapting sizes hopping. It's why these new data show us how the synthesis of nucleids has to be understood through the features of quasicrystals. Because the number of nucleids is limited. Because it takes special conditions to produce certain types of nucleids. And because the ratio of the number of neutrons on the number of protons follows a Fibonacci sequence to achieve the golden ratio.